The final section in the chapter on capacitance, chapter 24, is section 24.4. In this section, we look at capacitance values for other simple geometries. Now, these can be rather complex to compute, and so generally speaking, in the first course in physics, we just require that the student knows the parallel plate capacitor. But in slightly more advanced courses, we actually do the derivation of other types of capacitors. Here, we'll just give the formulas to show the difference between these. C for a parallel plate often written as this way, is given by, as you know, epsilon naught times A divided by D. This is the formula we just have been working with in the previous module. If we have a charged sphere of radius r relative to infinity, the capacitance of a sphere, and this is of course relative to charges at infinity, is going to be equal to 4 pi epsilon naught times r. Again, as I said, in the introductory courses we usually give these equations or just require the student to memorize them, whereas in the more advanced courses we actually do a derivation of this. Now we can look next at a capacitor that consists of a radius of an inner cylinder, and let's call this an inner and outer radius A and B. So the inner radius is A, and then we have an outer radius B. So this is what we call a cylindrical capacitance, and you can see here if we take charge off of this cylinder and move it out to this cylinder, or conversely, we can ask for the capacitance. This is what we called cylindrical capacitors. Cylindrical capacitors. And if they have a length L overall, then the capacitance can be computed to be L divided by 2K times the natural log of B divided by A. Kind of complex formula. But this is an important equation because very often we have a wire that's encased in some type of material like to prevent conduction, like rubber, and then on the outside of that we have a braided wire that is just shielding for that wire, and so we have a capacitance between those two that is important. Now if we take a sphere not relative to infinity, I'll put infinity here, but a sphere with another sphere inside, then it turns out that the capacitance, this is the inner is A, the outer is B, so this is A, this is B, is given by A times B divided by K, B minus A. So again, we have a nested pair of cylinders give this capacitance, a nested pair of spheres. A nested pair of cylinders gives this value. A single sphere relative to infinity gives us this value, and the parallel plate capacitor, which we always expect students to remember for the first course, is given by this equation.